Welcome to homework.
All right, in the problem, we're given a 2-meter long plank. So let's go ahead and draw the picture. It is not uniform, which is important because uniform objects have a center of gravity in their center. This one is not uniform, and they told us the center of gravity was 50 centimeters or 0.5 meters from the right end. So let's go ahead and draw in our gravitational force for the plank at that position. We draw the gravitational force there because the center of gravity is the point on the object that the gravitational force acts on. So that is 0.5 meters from the right end of the plank. All right, then we're going to have a box. The box is 75 centimeters or 0.75 meters from the left end. I'm putting everything in meters because we have to have the same units for all of our quantities. And physicists traditionally use meters, so let's put everything in meters. Then we're going to have a fulcrum, which is just a little triangular piece that's going to be at the midpoint of the plank. All right, they're going to take this box. The box has negligible mass, which means we don't need to worry about the mass of the box. And they're going to uniformly fill it with sand. Again, now that it's uniformly filled with sand, it means that the gravitational force will act at its center of gravity, which will be in the center of the box because it's going to be filled uniformly. So we can figure out the distance from the fulcrum of the box by looking at the width of the box, which is 0.75 meters. That means the space here is going to be half of the width of the box, or 0.375 meters. And the distance that's left here between the center of gravity of the box and the pivot is going to be 1 meter. I should put my units there. Minus the 0.375 meters or 0.625 meters. All right, we need to know this because our next diagram we're going to draw is called a torque diagram. Since this is an object that is capable of rotating, we don't want to use a force diagram because the force diagram just tells us the forces acting on this object. We can't shrink this down to a point mass, which is what we do with force diagrams. And so we need a torque diagram. And a torque diagram is basically a line representing the plank with the forces drawn on it at their specified locations. So we have the weight of the plank. I'm going to go ahead and put a subscript P there. That's our gravitational force of the plank. And we can find that by taking the mass of the plank times the gravitational field strength. Then we have this fulcrum here, and the fulcrum pushes up on the plank. We know it has to push up on the plank because the plank is not accelerating in the vertical direction. So let's go ahead and add that force from the fulcrum. We're going to call that the normal force because it's providing a support force. And it's normal because it's normal to the surface or perpendicular to the surface of the plank. And then we need to draw in our gravitational force that's acting on the sand. I'm going to call that FGS, S for sand, and we can find that by taking the mass of the sand times the gravitational field strength. All right, the last thing we need to do is to put our distances on here. So our distance for the plank is 0.5 meters from the pivot. It's going to pivot at the fulcrum. The reason we pick the fulcrum as the pivot point is because we don't know this force. This is an unknown force. And we don't know this force. This is an unknown force. So we have two unknowns. Well, we're not interested in solving for the normal force. We're interested in finding the mass of the sand. So we need to figure out the gravitational force from the sand. So we put the pivot at the center. That way the normal force does not provide a torque, and we don't need to know the value or the size of the normal force. All right, then last but not least, we put the distance of the center of gravity of the sand from the pivot, and we said that was 0.625 meters. Okay, now we can use our diagram to do our torque equations. Now we know that this needs to be at rest. That means the sum of the torques have to equal 0. We also know that we have two torques acting on this, a counterclockwise torque from the sand and a clockwise torque from the center of gravity of the plank. So the sum of the torques have to also be equal to that counterclockwise torque from the sand minus the clockwise torque of the plank. So that ultimately means that my counterclockwise torque must equal my clockwise torque. All right, we have an equation to find individual torques, and it is the perpendicular force times the distance from the pivot. Well, these forces are already perpendicular, so we don't need to worry about any sines or trig. So let's go ahead and put in our equations for our torque equations here. So I get the gravitational force of the sand, which is the mass of the sand, times the gravitational field strength. Let me write that a little bigger. Times its distance from the pivot. And that has to equal the mass of the plank times the gravitational field strength times the distance of the plank from the pivot. All right, we're trying to get the mass of the sand, so we are going to divide both sides by this gravitational field strength times the distance from the pivot. And that reduces to 1 on the left-hand side. The gravitational field strength reduces to 1 on the right-hand side, so we're left with an equation for the mass of the sand, which is the mass of the plank times its distance from the pivot over the distance of the sand from the pivot. We have numbers we can plug in here, so the mass of the sand is equal to the mass of the plank, which they told us was 25 kilograms, times its distance from the pivot, which is 0.5 meters, divided by the distance of the sand from the pivot. You can see that our meters reduce, and we're left with 25 kilograms times 0.5 divided by the 0.625, which gives us 20 kilograms. So if we want the plank to remain at rest, we would have to fill the box with 20 kilograms of sand.